So here's another pulley problem where you have two masses connected by this somewhat complicated pulley system, and this pulley is being pulled along by this force 200 newtons, and the masses are given, and maybe acceleration due to gravity is something. Okay, so how do we solve this problem? As usual, the first thing to do, or the second thing to do, depending on what you want to do first, is well, let's define some sign conventions. Let's say this is acceleration a1 in the positive direction. This is acceleration a2 in the positive direction. This is a sign convention, okay? So, oops. So this is sign convention for accelerations. Positive upwards is the sign convention, okay? Next, the next thing to do is, of course, draw free body diagrams. Let's draw the free body diagrams. I draw the slope with a dotted line because it's officially not part of the free body diagram. And then we have mass, let's say, m1, like so, which has, well, normal reaction n1, gravity m1g, and then some tension T1, let's say, up the slope, okay? And then we have, well, let's actually go one step at a time. We've done the mass. We have this rope and then this pulley. So let's do that pulley next. Okay, so because this end of the rope is connected to this mass, the tension is going to be the same, T1, T1, P, that's going to be that pulley, okay? And then this pulley is sort of connected to that pulley. So you have, it's the same T1 because it's the same rope, T1. And then this one is a different rope, so it's T2. Okay, so this is the second pulley. And then we have the other mass. We have this mass, which has, again, a normal reaction N2, mass M2G, and then the force pulling it up is T2, like so. Okay, so we've now drawn free body diagrams for each of these objects. The pulleys are massless, so it doesn't have mg down. And yeah, I guess these things are aligned with the slope. Okay. Any questions so far? Now, it is convenient very often to decompose this m1g into a mass component parallel to the slope and perpendicular to the slope. This is something you can try to remember if you want, but basically, if you have, this is basically the triangle that you care about. So this is theta. Oops. This is theta of the slope, and we have m1g. And so this is basically 90 minus theta. And if you say, what is this angle? That's going to be another theta. Okay. So we decompose this thing into, let me draw this a different color perhaps. We decompose this vector, m1g, into two components, one along this direction and one along this direction. So this angle is 90 minus theta, this angle is theta, okay? So what we have is this thing is equivalent to m1g sine theta and m1g cosine theta. So basically perpendicular to the slope, we have m1g cosine theta, and parallel to the slope, we have m1g sine theta. This is something that you can remember basically, where theta is the angle of the slope relative to the horizontal, okay? Of course, you can do this trigonometric decomposition if you want, but easier to remember perhaps. Okay, so we can do this for both this guy and this guy. So let me actually redraw this picture. So the two masses have free body diagrams that look like this. The red mass looks like m1g sine theta, n1 m1g cosine theta. Okay, so I'll be okay with it if you just drew this picture directly for something like this. Similarly, for the second mass, we have m2g cosine theta, m2g sine theta, normal reaction N2, and tension T2 pulling it up, okay? So these are the free body diagrams. Let's call this FBD1 for mass 1. Let's call this FBD2 for mass 2. This is FBD3 for pulley 1, and this is FBD4, okay? So now we can do F equals MA for each of these free body diagrams. Let's do the pulleys first because that's kind of convenient. If we do the pulleys, because the pulleys are massless, you have P minus 2T1 equals mass times acceleration of the pulley. But because the mass of the pulley is 0, basically P equals 2T1, okay? For FBD3 pulley, P minus 2T1 equals mass pulley acceleration of pulley. I'm just being informal here, and that's equal to 0 basically is the idea. So P equals 2T1. Let's call this equation number 2. And similarly, 2T1 equals T2. So for FBD4, 2T1 minus T2 equals, let's call this pulley 1 to be precise if you want, M pulley 2, A pulley 2 equals 0. So T2 equals 2T1, or T, yeah, I guess that's right, okay? So T2 is basically equal to P, I suppose, bringing 1 into 2, okay? Okay, so we have those two equations now. So let's call this maybe 2. Okay, so now we can write expressions for FBD1 and FBD2. So we have, let me just keep those pictures in there. So for FBD1, we have T1, so upslope, T1 minus M1G sine theta equals M1A1. Of course, perpendicular to the slope, we have N1 minus M1G cosine theta equal to 0. Because it's 0 acceleration. Okay, and then for FBD2, we have T2 T2 minus M2G sine theta is M2A. And of course, N2 minus M2G cosine theta equal to 0. Okay, this is upslope. This is perpendicular to slope. Okay, same here. This is equation 3, equation 4, 5, 6. I suppose we did not necessarily say what to find, but let's say we determine A1 and A2. So that's more or less it. We are mostly done here. A1 equals T1 minus M1 G sine theta. T1 is P over 2 divided by M1 from here. So that's the answer for A1. And then for A2 this is A2, T2 minus M2G sine theta divided by M2. T2 is just P, so we have P minus M2G sine theta divided by M2, and we can evaluate the answer. Okay, so let's just stop there. For this problem, by the way, we did not have to find a relationship between A1 and A2 because there were sufficient equations to actually be able to solve for all the unknowns. But in some problems, as in the homework problem, these masses are constrained in a manner that there is just one degree of freedom. In that case, you need to use a kinematic equation where you use the length of the rope to be equal to a constant to actually try to figure out another equation. So usually what I would say is first write down the free body diagrams and then write down the equations F equals ma corresponding to the free body diagrams, and then see if you can solve for the unknowns, count the number of equations and unknowns. If you can solve it, great. If you cannot, look for an additional equation that has to do with the length of the rope differentiated twice. Okay, so let's now stop.